Thank you, Lenka. So this is my second lecture. So the plan is to present rather fresh work. So it's the first time I present most of what I'm going to tell you about today. So it's going to be a bit less polished than yesterday, I think. You see it from this slide, maybe. So it's fresh, but maybe a bit raw. We'll see how it goes. All right, so remember the last time, what did we discuss? So we thought about deep learning, and we were really thinking about what happens when you change the number of fitting parameters, the number of parameters, by increasing the width of networks. Remember, n was the number of parameters, p was the number of data on which you train. And what we found is that was a tester. You want this to be as low as possible, is that very generically you would have this double descent curve. So what I want to talk about today, which I didn't mention at all the last time, is this asymptotic value here, right? So if you choose a very large number of parameters, and we've seen that in that case, deep learning can reduce to, depending on how you take this limit, you can have different asymptotic behavior, so you can have different test error. One case was lazy training, where you really behave like a kernel method. And the other was this feature learning regime, where you actually learn features. So actually, this quantity here will depend on which limit you take. So today, I want to talk about this. So this is maybe the practical question of importance. If you choose your architecture to have so large number of parameters, then what is the tester, and how does it depend on the number of the size of the training set P? Okay, so the more points you have, the better you will tend to do. How is this curve behaving? So one puzzle is really to understand why you can learn at all. So I mentioned it, that in large dimension, you have this curse of dimensionality, the fact that all your data points are very far away from each other. And in fact, for example, for regression, if you're trying to regress a function, if you assume that this function has very little structure, it can be shown that you cannot hope in general to do better than a tester, in that case a mean square error, that would go like the number of data p to the power minus 1 over d. If d is large, like a few thousandths, this is just a constant, so it means you're not learning, right? So one of the puzzle is, how do you manage to learn at all? And it's related to this question of how many data do you need to learn a task. Okay. So let's start maybe with empirical observations. So you can look at what's called this training curve, or that's a log-log plot, but you plot the test error as a function of the number of points that you have. And this is studied empirically, and typically what you see is that for large P, the curve can be rather well fitted by a power law with some exponent beta. And so in this paper, they study systematically many data sets. So for ImageNet, for the range of P they probe, they have beta between 0.3 and 0.5, speech recognition 0.3, language modeling 0.1, and so on. So beta is not universal, it depends on the data set, and it's probably just an effective exponent, right? If you could have billions of data, maybe this slope would change. But still, it's a useful characterization of what those curves are like, and it's a useful characterization of how well we do as we increase the number of parameters. So we want essentially to be thinking about this exponent. Okay, so this talk is, yes? Okay, so I will show you examples. So part of this talk is, so for example, in the feature learning regime, so I told you about two different regimes, this lazy training regime and this feature learning regime. And I will show you data there. Actually, Leonardo rapidly show you some data there, but for example, if you use a CNN on MNIST, depending on the regime, I will show you the data, but you find different apparent betas, right? So actually, it's part of the question I will be discussing in the second part of this talk. So in the first part of the talk, I want to discuss kernel regression, where you're trying to learn some continuous function. One of my motivation is that just a few months ago, I think there was a very interesting, important paper on this question, which is at least sort of partially, I think, solving the problem. I mean, at least recasting the problem in a way that makes it easier to track. So what I want to do there is first tell you about a simple toy model, a sort of teacher-student case where the function you're trying to learn is a random Gaussian field. So it has some covariance. And you learn that with a kernel. I will discuss maybe the simplest. OK, so where you can have if the teacher is equal to the student, it's base optimal, but you can also have a teacher and a student which are different. So here we sort of rediscover some more ancient work by Peter Solich, who was thinking about this problem in a physics way using the replica method or alternative approximation, which in finite dimension are not exact, but he was doing this. So what we entered this problem and came from a different perspective, looking at the Kriging literature. Geophysicists are also interested in that, where you simplify the problem by saying that maybe the point, your training set, is on a lattice, and then you can compute things. So we find the same asymptotic behavior as Peter, except that we find that there are actually two regimes. You can have good students or bad students, which was not explored before. But then I want to mention how these guys actually generalize. They look at Peter Solich's technical tools, but they generalize it to any kernel, any function. So that's a very general result. In terms of this problem of curse of dimensionality, what I would argue there from Zeus example is that at the end of the day, some kernel method can learn pretty well simple data set like MNIST and so on, but that's because for Zeus data, the distribution of the data is very anisotropic, and the true dimension of the problem is not that big, maybe 14 for MNIST, for example. Okay, so then so then in the second part of this talk, I want to go back to, do you think I could get a glass of water somewhere? Or sorry, I'm just a bit, I can go, but thank you, Leng. So I want to go back to this lazy versus feature learning problem. And there was a question just asked. If you look, for example, at rather modern architecture, I mean simple CNNs, not the most recent ones, but acting on, for example, MNIST, you will find that you have different betas depending on the learning regime. All of those benchmark models and so on, they are often on classification. So I want to think about classification where you don't have a general formalism like this one. So I will be thinking about very simple models. As they were again mentioned yesterday, but very simple models where you have symmetries invariance, and ask how those two regimes deal with that. And indeed, we'll find a model, a simple model, where those two exponents can be different, and where feature learning is better than the lazy training. Merci. Merci beaucoup, Linka. And this we put it on archive 2 months ago for the kernel regime, and then last month for the feature regime. And that's related to this notion that you're building invariant representation of the data in the feature learning regime. Yes?
So the 12-something beta is the exponent for the training error or the generalization?
Oh, that's always for the tester, generalization error. Oh. Yes, because in the over-parameterized regime, you bring the train error to 0. Yeah, oh yeah, sorry. So you bring the train error to 0, so you're in a regime where you're going to train perfectly. Ah, okay. So you would, so that's an empirical observation. If you had some mislabeled, okay, so if you had some mistakes in your MNIST, had some mislabeled, then you would think that it would plateau. But in practice, this is probably the quantity of mistake is too small to appear in this range. But you're right that if you had a finite fraction of mistakes, at some point this curve should plateau out. So that's why I'm saying it's an effective exponent, but I think the noise would it doesn't appear in the range of testers that we have. So it's
There are these recent papers about in mismatch that actually the fraction of errors in a mismatch or ambiguities rather than errors is super fine.
right. So I think if you start to reach this limit, if the tester starts to be of order of the mislabels, then you will plateau. But for this, you are still not there. Okay. All right. Okay, so yes, let's go to kernel regression. So you're trying to infer some true function, ft of x. X can be in d dimension, and you make p observation of what this function is. And I'm going to assume no noise here. And I think Florent told you about kernel regression. I will put no regularization here. And okay, so so K is your kernel. This K here is a Gram matrix that he also told you about. It's a P times P matrix whose elements are the K of xi, xj. This vector y is actually of dimension P. It's a set of observations that you have. And then you have this vector also of dimension P, whose components are K of x. You're looking at position x, xi. Yes? So I think that was discussed by Florent last week, if I understand correctly. So that's your guess on the function you're trying to learn for kernel regression. And there is one case where it's really good to do that. If it's actually the true function was a Gaussian field precisely of that covariance, okay? Then it would be your best guess on actually a posteriori what would be the mean of the function at that location. Right, so actually we will, to simplify, again, that can be generalized, but we will be, in the treatment I'm going to do, you can assume that the kernel, the function is a Gaussian field, and its covariance is just the kernel you're using. You can generalize it, and we did, but I'm not going to talk much about that. And in the discussion, I will look at specific kernels, which are called isotropic. So K of xy just depends on x minus y, like the Laplace kernel or the Gaussian kernel that you heard about. Okay? So first, let's again look at empirical, what happens if you look at standard benchmark and you do regression on them. Okay, so often we do classification. I'm going to do regression on them. So I'm going to binarize them. So mnits, maybe you have odd and even numbers. So my function f would be +1 for one category and -1 for the other. For cipher 10, we decompose the categories of picture of labels in two, and it's +1 or -1 as well. And again, in this case, the tester is a mean square error of your guess. Okay? And you can again look at this. That should be P. Sorry, we are ourselves not consistent with the notation. So this is again the same training curve. So this is the number of data that you have, and this is the tester. This is for Gaussian and Laplace kernel. This is for mnits, and this is for cipher 10. Okay? And this is again P, the number, the size of the training set. And what you find is that mnits is pretty well learned. I mean, you have an exponent that's rather large, O.4. It doesn't seem to depend on being Gaussian or Laplace. Cipher is already much harder. It's an exponent close to O.1. Yes? Yes. Yeah. Yeah, we do that, yeah. No? No, okay. All right. Okay, so now I want to present this toy model, teacher equals student. So let's think about f as being some Gaussian field, okay? I'm going to be looking at the case where in general key of x for small x close to the origin is a constant plus some non-analytical term plus some analytical term. So for Laplace psi is 1, you can have kernels for which this psi can vary continuously between 0 and large numbers. For the Gaussian, in those notation, it's infinity because everything is analytical, okay? So the game you're playing, so let me draw it in one dimension. Even I will do simple calculation. It's easy to extend it to find to any dimension, so I will just do it, but often I will draw or write equation for one dimension. So this is your field. You do those measurements, and you're trying to make a guess somewhere, and you ask, you know, what's the mean square difference between your guess and the truth in average. Okay, so obviously the more points you have, the closer points are from each other and the easier it becomes. So what we'd like to compute is this quantity, which is average on the disorder of the different Gaussian field that you have. You can average it on X or take a typical X. It doesn't really matter here. So let me first state what would be the simplest guess of what a kernel method would do. But the simplest guess is that you could look at the closest point and look at the variation between this closest point and the point you're interested in. And in average, this quantity can be written in terms of the kernel, and what you would get is this, and maybe you would guess that, okay, it would be obvious if psi is smaller than 2, so this is larger than any analytical term, then you would have this power of psi that enters here. In fact, and I will demonstrate why in the next slides, it's a non-analytical term that you should put here, right? Okay, but the simplest guess is that you're doing some kind of estimate from the nearest neighbors, and this term will enter in the performance. Yes?
This is like a random manifold, but it's planned. So you have like a noise, it's like an elastic spin, but the noise is planted by the example. So the correlation of the correlation of the disorder is given by the example.
So let's say you have a field that's taken from some Gaussian distribution, and then you start making observation on them.
Yes.
Because you observe them, conditioned to that, you learn more and more about what this function could be. And what you do in kernel regression, if the teacher is equal to the student, is that you can know in average where this function would be, but there is still some fluctuation about this average, and that's what I'm trying to estimate here with a simple scaling argument. Okay? So what you will get is then that essentially what controls the mean square error is a typical distance between points, this delta here, times this exponent psi. Again, so it would be sort of clear when psi is smaller than 2. Why it's true marginally, I will discuss on the next slide. Yeah?
What is the difference between F plus or FT and F?
So it's all FT. So sorry. Okay, so that should be FT as well, yes. Yes, there's only FT anywhere, yes. FT anywhere, sorry. Yeah. True function.
True function, okay.
So that's the true function you're trying to learn. That's your guess from regression. And here I'm just estimating the mistake by the variation of the function f on the characteristic scale that you probe when you have a certain number of points. All right, so this is, you would guess maybe that it's delta to the power xi, and delta in general goes like p to the power minus 1 over d. So it gives you a prediction that will end up being correct, okay, that this should go like p to the power minus xi over d. And you see already what's at play, that you have this curse of dimensionality here. If d is large, let's say if you are trying to regress a Laplace, for a Laplace, psi is 1, for example. So if you had a Gaussian field whose covariance was a Laplace, then you'd meet the curse of dimensionality. Your test error would decay like p power minus 1 over d. So large dimension is a problem. The only way you could fight it in this context is by having something that is extremely smooth in large dimension. So if you have this exponent psi characterizes how smooth your function is. If psi was of order d, extremely smooth, then you could beat the curse of dimensionality. But it would be a bit an awkward answer, right? If you have 1,000 dimension, you need to be 1,000 times, smooth to. Yes?
What is the tonality in this case? I mean, psi is infinite when you.
Right. So then it's not a power law. So for example, for the Gaussian case, it's not a power law. You don't have this exponent beta. I was telling you. Asymptotically, you do better than that.
You can run the argument in this case.
Okay. So yes, we discussed that in the paper, but it's exponential of something that's still very slow. So it's better. It's still bad, but it's better than a power law, asymptotically. It's still not good. Well, okay. Yeah, I can do it offline. I can. Okay. Okay, so let me give a marginal argument. And what's nice about this argument is that, okay, I'm trying to give a sort of super simple, I want to go towards this new result that those guys have, so I want to present this problem in a language that's similar to their language, okay? So let's think again about this problem. And, well, to simplify it, let's think that our field lives in a space of dimension L, which is periodic. So our function f is, it's a continuous function, but you could as well describe it by its Fourier components. And the Fourier components has to fit in this box, right? So you have an infinite number of Fourier components, and they are written like m to pi over L, okay? So inferring f is the same as inferring those Fourier components. Here is a simplification we're going to make. We're going to assume that you sample your function on a lattice, okay? So again, here I'm drawing it in 1D, but it's very direct to generalize it. So delta would just be L, the size of the system, divided by P, the number of data points that you have. Okay. So you're given your observation as a set of f of xi. This claim, okay, it's obvious for anyone who has done solid state physics, is essentially that if you sample f on a discrete lattice, what the information you will have is equivalent to having the discrete Fourier transform of this function f on this lattice for wave vectors that belong to the Brillouin zone. Okay, so it is stated here. So I can compute those discrete Fourier transforms. That's why here there is a D for discrete. It's not the same as this one. It's just defined as a discrete sum. You look at your f of xi, and you have this phase factor. But now m, k being in the Brillouin zone means that m varies between minus pi over 2 and pi over 2. Okay, so it means that your function f is defined by, an infinite number of wave vectors. But your observations are equivalent to give you the discrete Fourier transform of this function on the lattice for wave vectors inside this Brillouin zone. Makes sense? You have p observation, and here you have p such wave vectors. Okay? For a discrete Fourier transform, if I was going outside the Brillouin zone and computing these quantities, I will have just exactly the same value as if I was translating by 2 pi over n going in the Brillouin zone. So it would not give me more information. Okay? So now it's actually straightforward to, okay, so in this formula you could write f in terms of its Fourier transform by inverting this, and you would get the following. A discrete Fourier transform here for a given Km inside the Brillouin zone is just equal to the sum on all those green points. So you take the same wave vector here, but then you add to it all those terms of the continuous Fourier transform, right? Computed on an infinite sequence of terms. Okay, it's a few lines of calculation, but you obtain that. Okay, so those are essentially your observations. You have P of them. And they are expressed, they correspond to, and this is what you want to infer. And maybe what's important to note is that's an infinite sum. And each of these terms here, for example, a term here, it only enters in one discrete component. Okay? So at the end of the day, the problem is you observe that. How much can you infer from those coefficients? It seems like a lost cause because you have an infinite number of coefficients, but you have a prior. You know actually that these coefficients are decaying rapidly, and you know exactly how they are decaying. Okay. Okay, so you're trying to make this inference, and your prior is that, okay, because it's a Gaussian field, those quantities are Fourier transform is itself Gaussian. There are IDs, independent. And the thing is that you know that they decay rapidly as k increases. In fact, their variance is just the Fourier transform of your kernel. And in general, if you have a cusp in the kernel, that should go like k to the power minus d, the dimension plus this psi. Okay? Okay, so what happens is that if you take k smaller than, let's say you take k much smaller than this pi over delta, so some k over here. When you bring delta to 0, the next terms, those next terms, have much larger wave vectors, right? When delta goes to infinity, those wave vectors, when delta goes to 0, those wave vectors diverge, and so they become very small in this sum. So essentially, and that's, you have two regimes, I'm not going to discuss that, but if you have, say, a good student, so for example, if the teacher is equal to the student, but it's much more general. Bad students are those who believe that there is lots of power at high frequency. If you're a Gaussian, you're always a good student, for example. But for a good student, they will essentially reconstruct well this first guy, but there is no way they can reconstruct the others. Okay? So then the tester will be the sum on all the wave vectors that are away from the Brillouin zone of their square value. And just plugging that in, you recover what I had before. Okay? Again, there is another regime that you can look in this paper if you're interested in, but otherwise that's it. So you can essentially reconstruct your function at an infinite number of Fourier coefficients, and you could reconstruct essentially the first P of them, P being the number of data that you have. Okay. All right, so now let me talk about this paper, which is a few months old, but which I think is really interesting. And it claims to have a theory for kernel regression for any kernel. So even not, it could be, the neural tangent kernel of a CNN, say, or for any distribution P of X, and for any function. Okay. It's again made on some approximations that are not controlled. now they have a very recent paper saying that for isotropic distribution and d infinity in some scaling regime, okay, I can take question on that. They can be rigorous, but in general it's not. But if you look at their formalism, it predicts the tester without any test set, and you can test it on MNIST, and it works extremely well. Okay, so that seems to be, you know, in terms of estimating a priori the tester to be a very powerful, powerful work. So let me give you the idea. So, so when you have a kernel, you can diagonalize it. Okay. So, so what enters in this diagonalization is also the distribution of the data. Okay. And lambda would be the associated eigenvalue. In our case, what I discussed was thinking about a uniform distribution. So this was like a constant. Because this was just a function of x minus y, those were plane waves. Lambda was just the Fourier components of k. And okay, and then another thing is that in general, it's always true that your true function can be decomposed in terms of, this is an eigenbasis of functions. So you can always write your true function as a sum on, an infinite sum on the lambda of c lambda x. Yes? Yes. Yes. Okay. No, so that's a general, yeah, that's a general framework. So not Gaussian process. So f of t is not a Gaussian process for them.
Ah, okay.
Yeah. So that claims to be extremely general. Yeah. Okay, so they do some. Everything is formal. I mean, until you do some. At some point, you have to say that you have to take a mean on the disorder of, you know, where are your place points. And one way to think of it is that they have one way to build this approximation is that you have a fraction, and the mean of a fraction enters, and they take it to be equal to the fraction of the means. You know, so you're not allowed to do that. And also another way they can reach the same equation is by using the replica method, but you're not in infinite dimension. So, so that's why it's uncontrolled. So then probably it means you can find adversarial cases where it will work poorly. But the thing is that in practice, for real data, it works amazingly well, which is, I think, what we should care about. But it's true, you could think, how can I build counterexamples that way it really doesn't work? The only case where they can really make a formal proof, they told me, I didn't go into the proof, is when you take P of y to be uniform on a sphere, and you take the dimension to infinity, and you take the number of data scaling like a power of the dimension. And then the spectrum here becomes discrete because you have spherical harmonics. Actually, it's very similar to other works by, say, Montanari and others who look at polynomial fitting in those kind of limits. So that's also a way to obtain that rapidly. Then they can prove it. But otherwise, yes, they probably you can build at infinite dimension, probably you can build counterexamples where you find problems. But at least for real data, it's really amazingly working very well.
Why is this on level for R larger in the...
Oh, so you went already before me, right? So let me first go through it, right? Because, so you can decompose always your function like that. And in their formalism, they can express the tester from those coefficients C lambda. Okay? And that's what they tested. What we did, and they are also doing it in the new version of their paper, is to look at the asymptotic behavior of their equations. So their equations are not asymptotic. It's not only about predicting some exponent beta, but you can look at that. And under broad conditions, again, you could find counterexamples, but under broad condition, you find that the tester is just like what I told you before for for the random field, for the Gaussian field. For the Gaussian field, the test error was the sum of the coefficient in this decomposition. So essentially, you could fit the largest p coefficient of this decomposition corresponding to the largest eigenvalues. That's what happened for the Gaussian field. And so in their expression, you find a generalization of that. Whatever the kernel you have, you write it into this basis. And when you have p data, asymptotically, you will be able to reconstruct of order p coefficients. And the rest you can't. And so that gives you an error. So again, if you have a very, I told you when you have a poor student, it's not true. So here, exactly the same thing happens. You have another regime where it breaks down. But if you have a good student, you would get that. So that's something that we can.
You are not summing over all the coefficients. You are summing over the unit term.
So you're summing only over, well, if you don't have any data, okay. So you're summing over, so sorry, I went a bit fast. You can rank those eigenvalues by magnitude. So R is a rank. And essentially, what this is saying is that the first, of the order of the first p coefficient in largest, in rank, you can reconstruct, but the others you can't.
Okay, so you commit error on the other.
Yeah.
And so P, how do you,
Sorry?
how do you find what is P?
P is the number of test points. Okay, so this expression is a direct generalization of this. Okay, for a Gaussian field, this is just the coefficient in the so for a Gaussian field, once again, the eigenvectors are just plane waves, and the coefficients are just Fourier components. So when I said that you could not reconstruct more than the first p Fourier components, in this generalized language, it's just the same. It's saying that in this decomposition, you can just reconstruct well the first p coefficient when you order your eigenvalues.
And the kind of dependence on the dimensionality, how does it differ here?
Okay, so I will come back to that here, but here there is, it claims to be generic and not dependent on dimensionality. Again, they can prove it rigorously for in one special case for infinite dimension, but if you look at M-units, it works very well. Okay, so now I can tell you what we can. I'm going to use that to predict, in some sense, this exponent beta I told you about for M-units in cipher. So how do we do this? Let's assume that those coefficients decay like a power law of the rank. So the larger the rank, the smaller the coefficients are. Okay, let's assume something like that. Then if you look at this formula, it's obvious that the test error, just an integration, will be power law and beta is equal to 1 minus a. Okay? Now, to test those ideas, we just need to extract a numerically. So we need to measure those coefficients C lambda. Yes? To extract this exponent a. And in fact, that's something we can do with kernel PCA. And I was not really planning to explain it, but maybe I'll just take a few lines. What you have to do is remember this Gram matrix. You diagonalize it. It gives you some eigenvalues and some eigenvectors that are of dimension p now. And C lambda is essentially estimated by your vector of observation projected on those eigenvectors. And why? Because essentially, okay, I'm still going to say it, but diagonalizing the Gram matrix is very much like doing a sort of Monte Carlo estimate of this integral for a discrete set of points. Okay, so, all right, I would take more time to explain it but yeah, this is the thing to do, okay?
So A is there for all the coefficients.
Let's assume that, and let's assume that, okay?
Why R? R is the index.
R is the rank. So I'm just assuming, I'm looking at some cases. It's true for the Gaussian field, but let's assume that for my data, if I look at larger and larger eigen vectors and the coefficients, they decrease. And let's assume it's something like that. If it was something like that, I could, beta would be 1 minus a. Yes? So the point is that once we have estimated those coefficients, okay, our guess for the test error would be an infinite sum from to infinity of those coefficients. In practice, we cannot extract infinite number of coefficients, so we have another parameter. So it's like we take a larger training set of size n tilde, and we compute that. This is sort of the integral of, so when you compute this quantity on a log-log plot, the slope that you have gives you 1 minus a. So you can extract a from that if you want. So what you see here is this quantity, different colors corresponds to growing n tilde. So maybe you can just worry about the largest one that we have, which is this blue curve. Just by measuring this sum, you can extract a, which you find is 0.74 for mnist, and then you would predict that beta for mnist is 0.36, and it's very close to the 0.4 I told you about. Okay?
Confused what an M means? Like, how do you get the true function? I mean,
so you extract, you don't need to, what you extract just is your, what you have to measure are those coefficients. And I do that with kernel PCA. So that was the slides before. That was the slide before, right? So you do kernel PCA to extract those coefficients. And for sci-fi, you.
does the kernel PCA doesn't depend on the y, or does it? Is just the PCA of the input, or it also depends on the labels in kernel?
So sorry, you do kernel PCA to extract the discrete eigenvectors, and then you project it on your observation to get the coefficient. So this does not depend on your observation, but this does, because so then you can also measure a, which is close to 1, and that gives you a beta for sci-fi, which is 0.07, very close to the 0.1 that we saw. Okay, so that's again the statement that this way of thinking seems to be correct for those real data. And if you look at, so that's in our paper, but if you look at their paper, they look even at non-asymptotic aspect of that.
How do you get that 0.93 from the plot? Because everything goes down pretty fast. You just kind of look at it.
Okay, so we estimate this. Well, yeah, so I should be ashamed to put 3 here because it's not as precise as that, but you just estimate. You should try to bring n tilde to infinity. So you're trying to see when those curves start to look alike, and that's where you have confidence that you don't have finite size effect. And then you fit where it seems to converge in this region, right? So it's not super precise, but Laplace. Oh yeah, pixel. You have no notion of space here. You have no notion that it's a 2D picture. It's Laplace. The super naive thing, yeah. It's not an interesting kernel, CNN, blah, blah. No, it's just the Laplace kernel, right? It just plays with the distance between. So what I told you is that for Gaussian and for Laplace, you find the same. And this we expect because you, except if the student is very poor, the asymptotic behavior should be the same. Okay, so that we show it in our paper for the Gaussian, but also in this framework, it's also true. So that's why it makes sense that the Gaussian and Laplace lead to similar behavior.
In terms of computational power, like how much more simpler is it to estimate these coefficients with the kernel PCA than to actually run the kernel?
You mean? Okay, it's another question. You're saying, could we gain time by this idea? Or to
No,
no.
I think it like if I want to evaluate this test error with the method you described, like is it actually faster than just running the kernel method?
With a new test set? You mean to really... one way to estimate the test error is just to test your prediction. So I'm not saying... So here the idea is not that... I think it's not that you have a faster way to do that. It's that it's a theoretical way to understand where your test error comes from. And showing that, in fact, to compute your test error, it's just about understanding how your function decomposes into the eigenbasis of the kernel, right? So that's a theory, really, I think, more a theoretical insight than maybe a practical insight.
Because, I mean, the intuition would be that running the kernel PCA is basically as running the supervised kernel method.
So it's probably similar, yeah. I would think, yeah. No, right, so, yeah, this is actually the test error that you get with the test set. So I'm not claiming that you get this faster than that, but you don't need to add test point to have this, so it's a prediction on that. Okay, so that concludes. So it's like the other way around. So I had a joker because I was very fast the last time, so now I'm just halfway. Right, okay, so the conclusion for regression is that the test error is controlled by how you can decompose your true function in the eigenbasis of the kernel. In some sense, it solves the problem. It tells you what you should do to compute the test error. But on the other hand, yeah, like we measure this exponent A for MNIST and psi-far, but you know, what does it mean, really? And interpretation is a bit hard because in this diagonalization, the distribution of data P of X enters. And essentially, when P of X is uniform or spherical, then you can say things. But in general, I think we need to think more about this decomposition for models of data, or mixture of Gaussian, or whatever it is, you know, more generic P of X. Curse of dimensionality. So let me go back to that. And I think the Gaussian case was useful for this. So remember, the test error was going like delta, the distance between point to this power psi. And here we find that there is a paradox. We find that for MNIST, for example, the dimension is like 1,000. And if you were a Gaussian field in dimension 1,000, you need to be amazingly smooth. So does it mean that MNIST is that smooth, or what? How can it be that you find exponent beta O dot far for MNIST with a stupid, you know, Laplace kernel? But here, this is sort of giving the answer, because what really matters is the distance between point delta. So what tells you that delta should go like P power minus 1 over d? It would be true only if the data are sort of well isotropically spread. But in fact, you would expect that, no, they are very anisotropic and live on a manifold of smaller dimensions. And in fact, that's something that you can measure. So we are not the first one to measure it, at least for MNIST clearly. What you plot here is the distance between points, between your pictures, the nearest neighbor distance, right? You look at pairs of nearest neighbors, and you look at their distance with respect to the number of point P. And for MNIST, you find that indeed, in fact, it lives in a much smaller dimension than you would think. Actually, that's surprising that you find a nice power law for those 4 decades with an exponent that's close to 14. Whereas for psi-far, it's a harder problem, and I think that's why beta is actually much smaller, is that the dimension is more like 35. Yes? Yeah, for Laplace, psi is 1. Yeah, it's d plus 1 for in general. No, psi is always 1. Psi is always 1 for Laplace. The Fourier decomposition has an exponent that's d plus 1. But because you integrate on D dimension, it's
So is this a Euclidean distance? Somehow between a
yeah. This is just the Euclidean distance between points. So it's just saying that if you look at this Euclidean distance, the data are very anisotropic, and so so if you had a Gaussian field for dimension 14, you know, its smoothness would be just 3 or 4, something that's you know, not 1,000 to get similar result at MNIST. You know, so again, we need to understand much more what it means. The distribution MNIST, it's not a Gaussian field, blah blah blah, but it makes it reasonable that we get those kind of exponents. And there were similar conclusions reached recently by Gorbani and others about the fact that kernel method work when you're very anisotropic, but it was in a different scaling regime, which I will not enter into. Okay, so that was the part on regression, and now I was planning to talk about feature versus lazy training. Okay. So we discussed this question yesterday. It's believed that deep learning works well because you learn features that are some neurons higher up respond to abstract things that don't depend on many aspects, location, smooth deformation, blah, blah, blah. So all those aspects, you got rid of them. And so in some sense, you got rid of lots of useless dimension. So that's a way to reduce the problem of curse of dimensionality. Okay? It's not like what I described before. It's not that the data are anisotropic. The data are what they are, but there are directions in them where you have variance, but you have no signal, and you can get rid of those. Okay, so that's what we want to think about. Okay, so that's answering a question that was asked. How does this exponent beta I told you about depend on the procedure? And here, just look at those two curves, the blue one and that one. This is a CNN acting on MNIST. And what you see is that in this case, indeed, that's for the lazy training, so it's like a Gaussian method. Now we're doing classification, okay? So it's not really regression, but we find, so the tester now is just a priority to do a mistake. And we find that in that case for a CNN, the lazy regime is worse than the feature regime, and they seem to have two distinct apparent exponents. Okay? If data are a bit noisy, we need to have more statistics, but that's what appears effectively to be the case. Okay, so we're thinking about classification, and in that case, there is no general framework like the one I described before for regression. That's out there. So we'll be thinking about very simple models, and we want those models to have some symmetries, and see how different regime learns those different invariances. And here, which is a bit different from what's usually done in the literature, again, we want to look at the limit where D is finite, and P varies and can be large. And that's motivated because for MNIST and CIFAR, we find that, you know, D are small, but P can be 10 power 4, 10 power 5 even, right? So we want to look at that, and in this regime, we cannot use like exact calculation, so I will do scaling arguments, you know, like we like to do in physics. So non-rigorous, very non-rigorous, but then they are predictive, and then you can compare to, empirical results and test them. Okay, so the kind of model I want to be looking at is think about the input space as decomposed in two. I will call this parallel space and orthogonal space, and they have two dimensions that add up to D. And here my label only depends on one of those spaces, X parallel. So if you want, it's only X parallel that contains information. For a network, this stuff is noise. So it's going to affect your output, but it has no information in it. All right. So I should mention that there was a very nice paper by Lenaik and Bach on similar question, looking at worst case settings. So it was not estimating betas as I want to do here, but that's a very nice paper. And comparing feature learning to the lazy training regime. Okay, so example of models. So the simplest one would be if you have just one direction that's informative. One model, for example, would be the stripe model. The only thing you can do then for classification is to have a bunch of interfaces separating labels of different signs. But you could think about, say, a cylinder. Then this would be the informative direction. This would be uninformative, you know, all those kind of models. And here I will first assume that P of x is Gaussian, so it's symmetric around 0, okay? So those are my data, okay? So they don't know, the distribution of the data doesn't know about the distribution of the labels, okay? Doesn't know about x perpendicular and x parallel. Okay, so those kind of models display what we want in some sense. Here again, you're just supposed to look at two curves that were, again, they were shown to you yesterday. So you're learning a network on, this is for the stripe model, so the one where you have stripes like this. And you're learning those data with networks that can act in the lazy training regime or in the feature learning regime, okay? That's done for different dimension of space, but in fact, we think dimension doesn't matter. I will argue theoretically what we get at the end. I mean, it does matter, but at the end it can be very large and it would still be true. So, so we do find here that it captures the fact that in the lazy training regime, you have an exponent which is beta, which is smaller, meaning you learn less well than in the feature learning regime, okay? For a cylinder, we find similar picture, for example, but with different exponents, and we think we understand why. So what I want to do now is to tell you in this simple model what controls those exponents, okay? Again, it's in finite dimension. We don't have exact result. It's going to be about scaling arguments. So let's think about first kernel learning, okay, for classification. And the connection is that, for example, if you look at a fully connected net with ReLU nonlinear functions, it's very similar. Asymptotically, it would be the same as the Laplace kernel. It would have the same cusp close to the origin, which controls what we're going to be talking about. So I think Florent told you about support vector machine, right? So in support vector machine, and it's going to be very similar to what those nets do. In fact, empirically, we find the same exponent in both cases. What you do is you look for a function that can be written in terms of this. So again, you play in a space of function of dimension p, which are written as k of x minus xi. So yes, I will be looking at, let's think about the Laplace case where k of x xi is a function of x minus xi. Here, alpha I, sometimes I call it the charge because it's very similar to a problem of electrostatics. Yi is a label. You minimize some kind of norm, which I didn't even write here. Probably Florent told you about it, with some constraint. And those constraints are that those coefficients are strictly 0 if you fit well this particular data by a margin 1. So it's very much like the hinge loss I told you yesterday. If you fit your data by the margins, then it exits your loss. So here it exits the function. The alpha is 0. But in the other case, where you're just marginally fitting you're right at the margin, and then alpha I can be larger or equal to 0. Well, maybe I should not. I will. Okay, we'll see. We'll talk about dipole maybe briefly. Okay, I like this. No, okay. Okay. Depending where you come from. Yeah. Well, you can think. Okay, you can think of it as your. Well, we'll see. Maybe I can comment more. And then you call it a support vector. All right. Well, there is a very simple, boring case. If your kernel starts to become like a delta function, for example, if you look at a Laplace kernel and you take sigma to 0, then essentially points affect f only locally. So it's going to be for the positive label, it's going to be +1. For the negative label, it's going to be -1. But then this would start to look like delta functions. So in that case, points don't really affect other points, so every point needs to be a support vector. And in terms of this algorithm, if I take a random point somewhere and I ask what's the sign of f, it would be dominated by the nearest neighbor data. So in this case, you're doing nearest neighbor algorithms. And even for the simple data structure I told you about, it works very poorly. So the test error goes like p to the power -1/d. So I want to be looking at the other case where this sigma is large. And then what will happen, for example, if I have a boundary between plus and minus labels. So sorry, sigma is just what enters in the here. It's called what, the length, or what, there's several names. But so let's think of it to be large, okay? Then what will happen is that you will have support vector where fitting is difficult, in fact. So for example, if you have an interface here, around there you would have support vector around here as well. If you are looking at what the function f is doing, it would be large and larger than 1 away from the interface, so you don't need to worry about that. They are not support vectors. Then it would have fluctuation and be of order 1 in this region that delta will enter in my scaling description, and then it will be smaller than -1, okay? So we looked for, in this limit where you have finite dimension, this exponent beta, even for the simplest case, like one interface, we couldn't find in the literature those results for the rate for the exponent beta. So what you would find in the literature are, again, this limit p over d going where each go to infinity and alpha is finite, but it's not really the limit that we want. And what you find are bonds in the kernel literature based on capacity. And with that, actually, you can prove that those problems I'm telling you about are not too difficult for kernels. You can prove that beta has to be larger than 1/4, for example. We did it based on their theorem, but I mean, so the classical literature would tell you that you don't have the curse of dimensionality for the kind of data we're looking at.
But even though with the scaling receivers, if k is sufficiently large, that's like large sigma.
Okay, so here the goal is, I don't think the goal is to find the best algorithm. For one thing, the perceptron has a better prior on a flat interface, right? So here we're really trying to think about.
Yeah, I'm just trying to understand why the nearest neighbors would have the curse of dimensionality, or if it is inevitable, or if you scale the k in some way, if it goes away.
So I can argue why it's the case where if you have a small sigma. Now maybe you can build algorithms where you look at more nearest neighbors. I didn't think about it, but maybe we can talk about it after, because I still have like a certain number of slides. And so here I'm just going to do simple scaling arguments to think about that. That seems like a very basic thing to do. What fixes the tester? So I'll just give you the main ideas. So we look at large sigma, so we can actually expand this k of x. And again, I allow myself not only to deal with Laplace kernels, but I could have this matter kernel where psi can vary continuously. I'm not going to keep track of this sigma because I'm just interested in the scaling with the number of points. So when I add this expression for f written in terms of the kernel, if I do this expansion, then my function f will be a function of that type, okay? So let's look at one interface. You can extend this result at several interfaces. The exponents do not change. The prefactors are interesting, but I'm not going to talk about that. So we do scaling. So what we want to understand is what's the typical distance delta on which support vector exists. And I will also call alpha the typical value of those quantities, okay? I want to know how those scale with the number of points. So there is a first scaling relation that's easy to obtain. It's what I told you before, that this is the scale where f varies between +1 and -1. And in fact, so this is a statement that if I look at the derivative of f in this direction times delta, it has to be of order 1. So it turned out that for large p, this becomes completely deterministic. It's even not a fluctuating quantity. And you can estimate, so I'm going to do scaling, how that scales. There is the number of support vectors that enters is proportional to p delta. Okay, just because you take the gradient of that, the number of terms in the sum is going to enter. Alpha is there, so it enters here. And there is also a geometric factor delta that enters because you're looking at the gradient of this function in that direction. Look at those terms. If you had a support vector here, it's radially affecting this point, so you'd have no effect there. So you need, a finite delta to see a gradient, and that's why you have this additional delta factor. I'm going fast, but okay. So then you would get that p alpha delta cube goes like 1. That's your first scaling relation. Okay.
The number of support vectors should be equal to number of data points, right? It's the projection of the...
Oh no! All those points there are not going to be support vectors. You will have support vectors just in a very narrow strip around your interface. Actually, we'll find that those interfaces where you have support vectors are extremely tiny, and the distance between support vectors is much larger. So you manage to build an interface with just a few support vectors like that. So one thing that enters in the argument is the distance between support vector. So let's assume it's thin. Okay, it will turn out to be the case. It's just the usual argument in d dimension. It goes like p minus 1 of the number of points power minus 1 over d. Here you live in dimension d minus 1 because you remove that one. And the number of points is proportional to delta p now, so that's how this scale, the distance between support vector, is going to scale. It's a very simple geometrical argument that gives you that. And the last argument that you need to close the loop is this argument, is that how much f fluctuates as you move, for example, along this line. And what you find is that I told you the gradient in that direction does not fluctuate, but here the function has to be -1, and here it has to be +1, and the position of those guys fluctuates. So what it means is that when you move along these guys, the fluctuation of f is of order 1. And that has disappeared, but what it means for your decision boundary, that it's making fluctuation of the size delta here. So you get that the test error is going like delta. And then just from this argument, you can close the loop and find the missing scaling relation. But it's a bit complicated to do. So in fact, what we find is that there is an additional hypothesis that gives you the correct scaling very rapidly. And it's the hypothesis of minimal perturbation. Think about, you have a solution of your problem, and then you come back and you add 1 point here. And you ask, how much is it going to change the solution? We're going to assume, and we test empirically, that it's not going to completely destroy your solution everywhere. It's going to do a sort of minimal perturbance. And the minimal thing you can do, if you add something here, the function will have to change by something of order 1. Not to have effect at a distance, what you can do is a dipole. You look at the neighbors there, and you're going to remove some charge here and add some charge there to lower the effect of this guy. The magnitude of this dipole has to be strong enough to make this guy change by order 1, and this is the magnitude of a dipole, and so you get that alpha RC per xi has to be of order 1. Okay, if you're interested, you can look at it. I understand it's going fast. But that's the thing that you can then completely test empirically. So what you would get at the end is that the test error that goes like delta. Now you close the loop. You can see you had 3 unknowns. You can solve it. We can compute this exponent beta. It depends on dimension and psi. And it's in infinite dimension goes to 1/3, which is fortunately larger than 1/4. which was the bound from the kernel that we can get from the kernel literature for this model. And you can test it. This is tested between dimension 2 and 30, and you find that it appears to work very well for all those quantities I told you about. Okay. So that's for really, those tests are for really SVM with the Laplace kernel acting on the stripe model. But now I can go back to the same model, but learned by a network in the kernel regime. And this is the curve I showed you before. And this is our prediction for the exponent that seems to be close to what we see. Okay? So we understand this part of the curve. So now we'd like to understand why feature learning is doing better and how much better it's doing. So before I do that, I have to tell you about compression. So all those scaling arguments, I've done them in the case where it was isotropic, the distribution of point. But now you can smash it by a factor lambda. So now it's an ellipses. And you can redo all the arguments, all the scaling arguments that I told you about, and you find that the test error still behaves in the same way with the number of points. It's the same exponent, so I didn't rewrite it. But you have a prefactor lambda with some power of d and psi that enters here. I'm going to use it in the next part of the talk. But okay, so it's the same set of scaling arguments that you use in a different geometry, and they give you how the prefactor will behave. Okay, so now let's go into this feature learning regime. Remember, your function that you're learning is just how we initialize those kind of one hidden layer nets, except that I put this alpha factor in it. If alpha was order 1, when the number of neurons was going to infinity, I was recovering the kernel. But here, I want to be in the feature learning regime. I told you it's just enough to take alpha going like 1 over square root of h to be in that regime. The argument we have is even more extreme. We take this quantity alpha square root of h being much smaller than 1. So you can really think that we're initializing the network to be extremely small, with extremely small weights from the beginning. Okay? And then what would play, so W, vector W is, if I look at one given neurons, it's how its weights. And you can itself decompose it into a parallel direction and some orthogonal direction. And you can define this factor lambda. So what you would like to have is, what you would like to learn is to have strong weights for the informative parallel direction and have small weights for the orthogonal direction, because this orthogonal direction is just noise with respect to the label. So if you keep weights in that direction, it brings noise to the output. It's not so good. So that's what I just said. In fact, if you were contracting all the orthogonal weights by a factor large lambda, in terms of the output, it's completely equivalent to take the distribution of the data and itself compress it with the same factor. Okay? So that's why we call it compression. By compression, we really mean sort of geometrical compression of the data distribution. So here are the results. If you have an infinite number of data, we find that lambda goes to infinity in this limit. And why is it so? That it's just you started with very tiny weights, and the gradient on the bad weights is, if p is infinity, is just 0. So you have gradients on the correct direction. You don't have in the bad direction. If you start from something that's essentially 0, this ratio would be infinity. Okay? By contrast, if p is finite, the gradient here is not going to be 0 because you have sampling noise. And what we find then is that this compression factor is limited by noise, and just by usual central limit theorem, as you would expect, we find that it goes like the square root of p. So it's a finite size effect of the training set that limits how much compression you have. Okay, So now we can make the following assumption. We can test the idea that in those models, at least, I don't think it's going to be completely general, clearly, but that in those models, the benefit of feature learning is to do this compression. So how do we test that? Well, instead of doing feature learning, where we do feature learning, and for a given p, we get this compression factor, okay? Then we go back to our data, and we compress them by the same factor, and then we run the network, but in the lazy training regime, where it's a kernel. So if really feature learning is good because it compresses, then the two procedures should lead to similar test error. And that's actually what we find. So this is the feature learning regime, and this is the lazy regime, but once you compress your data by the same factor. Okay? With this idea, you can, and what I told you before, you can reconstruct what this exponent, because I told you that if you compress, you have a prefactor that enters. That was my usual kernel result. If I compress by some factor, I have this additional factor in it, and I know that lambda goes like square root of p. So at the end, I have a prediction in this regime, which goes like this, and for large dimension, I find that beta is twice larger here than there. Okay? Okay, so now I have 2 or 3 slides of conclusion. So what we observed is that for a CNN on MNIST, for example, feature learning was working better. The exponent beta was better than in lazy training. This fact is captured by these simple models where you have invariance. And really what happens in this model is you compress the directions that are uninformative. And an interesting result that we have is that this compression is limited by sample noise. Something I didn't talk about, but Leo talked about it, is that those models are also interesting because this compression has very marked features in the evolution of the kernel in time, this neural tangent kernel in time. But I don't want to repeat what was said. So the main conclusion overall with respect to this curse of dimensionality, well, one first idea that if the data are very anisotropic, then even kernel method can do well because the problem is not really in high dimension, okay? So that's, but if it's not anisotropic, if you have, so the data are isotropic and maybe in large dimension, but if you have invariance in this feature learning regime, you can essentially compress those directions where you have invariant to effectively reduce the dimension of the problem. And this compression is limited by sampling noise. And now let me just conclude with some questions that are still there. So one question we raised the last time, which is as puzzling as before, is that it's all nice, but why is it that feature learning is worse than lazy for fully connected nets on real data? Because I was looking at fully connected on a very simple model, and it was doing better, but for real data, it's not. And I think it's also related to the question of invariance. So we looked at very simple invariance, an aspect of the data that are unrelated to the task, like a pixel very far away from the image. But clearly you have other class of invariance, you know, translation, diffeomorphism, and things like that. And I think we need models that really deal with that. Okay, I'm done. Thanks.